In today's lesson, I am going to show you the link between enthalpy of solution, enthalpy of hydration, and the enthalpy for the lattice energy, and how those three different processes come together in sort of a mini Hess cycle, and then an equation can be derived for that Hess cycle, which is then used to calculate enthalpy of solutions, hydrations, and lattice enthalpies for various problems. So let's take a look at this question. Draw a Hess cycle for the following three processes. So number one, we have A plus B minus goes to AB solid. Number two, the gaseous ions are becoming aqueous. And then number three is the solid AB dissolving to form aqueous ions. It doesn't actually matter which equation I put as the top one. So I'll just put number one. So it'll be A plus B minus goes to ABS. And the way to sort of create Hess cycles is to look for links between the different processes, right? So I can see, if I get a different color here to show this, I can see that AB solid is produced in reaction number one. And I can also see AB solid is being dissolved in reaction number three, in process number three. So there's my link. So I can go ahead now and I can do an arrow going down from this side to produce A plus AQ plus B minus AQ, which is this process. So there's those two processes done. Then finally, we can see equation number two is the gaseous ions becoming aqueous. So my arrow for that process is simply down. Right, now I can reveal the names of these processes, which you've probably already spotted what they are. So the first one is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions. And this is known as the lattice enthalpy, the enthalpy of lattice. So I'm just going to call it LE. Then the second process is the gaseous ions becoming surrounded by water molecules. Now that is the enthalpy of hydration, which I'm going to write as delta hyd. And then number three is the solid compound, or the salt, dissolving to form aqueous ions. In other words, dissolving a salt in water. So that's the enthalpy of solution, which I'm just going to write delta H sol. So I'm just going to use my notations there, shorthands, to create this equation. But before I do that, let's put the labels in. So this one is LE. This one going down is hyd. And then this one is the solution. So if I write an equation now for that mini Hess cycle, and then just to summarize what Hess law is about, so the enthalpy change for a reaction is independent of the route by which it takes place. So it doesn't matter whether we go, just to use a different color again, it doesn't matter whether we go directly from reactants to products or indirectly, which would be down, across, up. The enthalpy will always be the same. So we have, according to this equation, this top route is the direct. Going down, across, and up is the indirect route. So let's put along the top, we have the lattice enthalpy, LE, is equal to, if we go down this way, you can see that black arrow there is running the same direction as the red arrow. So it's the hydration enthalpy. And then we go across and then up on the other side. But you can see, to get from the aqueous ions to ABS, this arrow here is going against the direction of that arrow. So I need to reverse the sign of the enthalpy of solution. So it'll be minus delta H sol. Now if I rearrange my equation that I've just made there, I end up with, to make delta sol the subject of the equation, delta H sol is equal to the hydration enthalpy minus, I'm taking the lattice enthalpy over the side, minus the lattice enthalpy. And that is my final expression there. So the enthalpy of solution for a salt is equal to its hydration enthalpy for the ions involved in the salt minus its lattice enthalpy. And then what happens is this will produce a value for the enthalpy of solution that can be either positive or negative, depending on how the hydration and lattice enthalpies play off of each other. Just to summarize, if we have the process and then the sign, so the enthalpy of hydration, which is the enthalpy change when 1 mole of water molecules hydrates, gaseous ions, is always negative. It's always exothermic. The reason why is because the water molecules are basically forming hydrogen bonds with the ions, right? And that, so they're forming these electrostatic attractions, and that releases energy, so it's exothermic. So the hydration enthalpy, always negative. The lattice enthalpy, so delta HLE, that too is always negative, because when you form 1 mole of an ionic compound, energy is released when the ions attract each other. So that too is always going to be an exothermic process. Now the enthalpy of solution, which is the one we just derived the equation for, well, that depends. It can be positive or negative. And it depends on, as I just said, how the hydration enthalpy and lattice enthalpy play off of each other. And it really does vary from group 1 salts, group 2 salts, group 3. It is pretty much different every single time. Now, what does this look like in a question? What will an A-level question ask you about this? How do you put this knowledge into practice? Well, the answer to that is in the video I've produced, the link of which is in the description below. Go and watch that, put this knowledge into practice and see what an actual past paper question looks like when it's about the enthalpy of solution. Let's get on to the next one.